All right, guys, today we are going to learn about kinetic molecular theory in Gen Chem. And you have probably seen a lot of this before. So this should seem fairly familiar because a lot of this is talked about in your 8th grade science core already. So let's break it down really quickly. What are the 3 basic states of matter? And sometimes we use states, sometimes we use the word phases. So I want you to also know this word, phases, as well. So what are the basic states of matter? You probably can name them right off the top of your head. Solid, liquid, gas, right? So we have solids, and we designate that with a little s in the middle of parentheses. We have liquids, and we designate that with a little L in the parentheses, and gases. And we designate that with a little g in parentheses. Okay, so let's talk about the properties of each of these phases or these states of matter. So solids, they have definite volume. Okay? They have a definite volume, which means that their volume can be measured. I can measure their volume. Because they also have a definite shape, right? I can put, for example, this water bottle, it doesn't change shape unless I hit it really hard and change the shape of it. It has a definite shape. It doesn't change regardless of what I put it in. Okay, that definite shape comes from a couple of things. It comes from having a crystalline structure. So if I actually looked on an electron microscope on solids, I would see a regular repeating pattern that will show me a crystalline structure on a solid. Now, we normally don't think of all solids having a crystalline structure, but they really do. They're crystals, okay? And then that definite shape means that the molecules don't move very much. They do move, but the molecules move or they vibrate around a fixed point. So the particles, being it molecules or atoms or ion, those particles vibrate around or about fixed points. Okay? So another thing that definite and that vibration around that fixed point means that the molecules in a solid cannot flow. So they cannot flow. Okay? They're rigid. Okay? Solids are not compressible. So I can't smush the molecules closer to each other than they already are. Okay? And the molecule's kinetic energy compared to liquids and gases are really low. Okay? So if I drew a picture of a solid, and if I drew the molecules in that solid, I would have little molecules that would line up perfectly with each other and create these perfect crystal structures. Okay? They would be perfectly crystalline, perfect order, nice and neat. Okay, liquids. They're a little bit different. They do have definite volume. Just like solids, they definitely have definite volume. Like if I have this liquid in my water bottle, I can definitely measure the volume. But if you notice here in this liquid, I can change the shape. Depending on where I move this water bottle, the bubble moves around in it. Okay? So there is no definite shape. That is because those molecules can slide past each other, meaning that they can flow. So liquids flow. Okay, so there's no crystalline structure. And because those liquids can slide, those molecules can slide past each other, it means that the particles are moving around each other. So the particles they vibrate still, but they vibrate about moving points. So the particles vibrate about moving points. So they can flow, okay? But the particles are still relatively close to each other in liquids. So they are also not compressible. There is not much space between the molecules, so I cannot push them closer together at all. Okay, so if I was to draw a picture of a liquid, I would have molecules just kind of around. They'd be close to each other, but there'd be no particular order, okay? So notice they're not in a nice line like they are in the solids. They're close to each other, but there's no particular crystalline order to those molecules, okay? Now gases. Gases, actually, I want a pen. Gases. There is no definite volume. Gases will expand to fill up their entire container. So there's no definite volume. Okay. If I blow air into that balloon, the air that goes into that balloon is going to expand as much as that balloon lets it expand. Okay. It's not just going to stay in one portion of the balloon and the other half of the balloon is going to be flat. Okay. And there's no definite shape. Okay. Gases can flow. The molecules can move past each other, move all around, okay? So there's no crystalline structure. In fact, in gases, there's no structure, okay? The particles have constant random motion. They're going all over the place. Okay? Now, the other thing about gases is the particles are really far apart from each other. So because they're far apart from each other, it means that gases have a lot of empty space. So particles are far apart from each other. So it means that gases are mostly empty space. Okay, so if I drew a container of gases, I would have molecules randomly moving about. So these would be moving all over the place in that container, and they would be moving relatively quickly. There would be a lot of space in between those molecules, okay? Lots of random motion. Okay, I think that's what I want to say about solids and liquids and gases. So now I'd like to define the kinetic theory of matter. And my computer just jumped. Okay, let's see if it will jump back. Maybe not. Okay, so the kinetic molecular theory is based off of the Greek word kinetics. So kinetics if I look up the Greek word kinetic, kinetic means motion. Of course, let's just jump back. Sorry about this. Okay, so kinetic is Greek. It's Greek, and it means movement or motion. So the idea of the kinetic molecular theory is that we are going to describe how things behave, solids, liquids, and gases, based on the movement or the motion of the particles that make up solids, liquids, and gases. Notice how a lot of these defining things that I just said about solids and liquids and gases were about their motion and how they can either move against each other or not. Okay, so there are a couple main ideas of the kinetic molecular theory. Okay, the first main assumption of the kinetic molecular theory is that all matter is made up of particles. Now, those particles could be atoms, they can be molecules, or they can be ions. Okay, so all matter is made up of atoms, molecules, or ions that we can think of as individual particles. Okay, the second assumption of the kinetic molecular theory is that all particles are in constant motion. Okay, so all particles are in constant motion. Now, if you noticed, I said solids were in constant motion because they vibrated around fixed points. Liquids are in constant motions because they vibrate about moving points. And, excuse me, there's the bell. And gases are in constant random motion. Okay, so we are describing all of these through the motion of those particles. Okay? So that is the kinetic theory of matter. The other idea is that when particles collide with each other, the collision is what we call elastic. And if I have a collision that is elastic, it means that when I collide with something, no energy is lost. So kind of like if you've ever played air hockey, if that air hockey table is working really well and you hit the puck, that puck is going to bounce off the sidewall or the back wall, whatever, and it's still going to be traveling at the same speed before it was hit and after it hit the wall. That means no energy was lost. So elastic collisions mean after the collision, the energy is the same as the energy before the collision. So no energy lost. Okay? So let's think about temperature. What happens to molecules when we raise the temperature? What happens to their motion? Kinetic energy is really a measure of temperature. Motion is a measure of temperature. So when things get hotter, don't they move faster, right? So as temperature raises, as temperature is increased or raised, the energy of the molecule is also raised. Okay, so that means the kinetic energy, and I do this for kinetic energy, is also increased. So that means temperature is a very, very good indicator of how much kinetic energy a molecule has. The hotter the temperature, the more kinetic energy. The colder the temperature, the less kinetic energy, the less motion those molecules have. Okay? All right, think about this. How cold would it have to be for the molecules to absolutely stop moving? Okay? Theoretically, if the atoms or molecules that make up matter have absolutely no motion, they stop moving, their kinetic energy would be zero, right? So if they stop moving, no kinetic energy. What type of temperature would this be? It has been found through experimental evidence that all matter will have a kinetic energy of zero if the temperature is 0 Kelvin. And I don't know if you've heard of the Kelvin scale, but 0 Kelvin is extremely cold. That's where no kinetic energy exists. That's about negative 273 degrees Celsius, or about negative 419 degrees Fahrenheit, if I remember correctly. Okay, I'm going to have to check that on the Fahrenheit because I'm a scientist. I don't use Fahrenheit. Okay, so this idea of zero kinetic energy is called absolute zero. Okay, so the temperature scale is basically a scale that we use that measures things based off of when they are absolutely have no kinetic energy and up. There is no negative value in the Kelvin scale. Okay, so the Kelvin temperature scale, negative 273 Celsius is 0 Kelvin. Notice that there is no degree mark or no not mark when using the Kelvin temperatures. It's just K or Kelvin. Okay? So to find the Kelvin temperature, I simply have to add 273 degrees to the Celsius temperature. To find the Celsius temperature, I'm doing this backwards. Oh my. To find the Kelvin temperature, I have to add 273 to the Celsius. But if I want to find the Celsius temperature, I have to simply subtract 273 from the Kelvin temperature. And I would say from the Kelvin temperature. Okay? So here are the equations right here. If I want to find Kelvin and I have Celsius, I'm going to add 273, just like we said here. If I want to find Celsius and I have the Kelvin, I have to subtract 273, just like we had here. Okay? So we're going to convert the following temperatures from Celsius to Kelvin, Kelvin back. Okay? So if I have 0 Celsius and I want to go to Kelvin, I have Celsius and I want to go to Kelvin. So I'm going to use this first equation. I'm going to add 273. So 0 plus 273 is 273. Okay? I have Celsius and I want Kelvin. So I'm going to use that first equation. So 25 plus 273 will give me a temperature of 298. Okay? My computer doesn't want me to write. So this first column, we're just going to add 273. So if you start with Celsius and you want to go to Kelvin, just add 273. So minute still. So 25 plus 273 is 298. Okay, so if I have negative 55 plus 293, or 273, sorry, is 218. Okay, and 223 plus 273 is 496. Okay, how'd you do on that? Now the second column is going to be the opposite. We are given Kelvin, so we need to subtract 273. Okay, so 15 minus 273 will give us negative 258 Celsius. 298 Kelvin will give us 25 degrees Celsius. Okay, so 298 minus 273 is 25. 337 minus 273 gives us 64 degrees Celsius. And 147 minus 273 gives us negative 126 degrees Celsius. Okay, so that is how you convert from Kelvin to Celsius and Celsius to Kelvin. Okay, next time we're going to talk about the mass and speed of particles and talk about some of the different ways that we can use the kinetic molecular theory to understand phase changes, going from solids to liquids, liquids to solids, or liquids to gases, and vice versa. We'll see you later. Bye.